Section 4.3, Derivatives and the Shape of a Graph. For our first theorem, we have the increasing-decreasing test. It says that if the derivative is positive on an interval, then f is increasing on that interval, and if the derivative is negative on an interval, then f is decreasing on that interval. We can see this by letting x1 and x2 be two arbitrary numbers on an interval where the derivative is positive, such that one of those numbers is bigger than the other, so x2 can be bigger than x1. Then by the mean value theorem, we get that those two y values, when you subtract them, are equal to the derivative at c times x2 minus x1 for some c in the interval. Remember, that's the same thing as saying if we divided both sides by x2 minus x1, the slope of the secant line would be equal to the slope of the tangent line for some c. But f prime of c is greater than 0, and x2 minus x1 is greater than 0, because that's exactly what we're assuming. We're assuming the derivative is greater than 0 in that interval. So that means that for a single value in that interval, the derivative must also be greater than 0. This thing must be greater than 0 because we said, by assumption, make one of them bigger than the other. Okay, so if this thing is positive and this thing is positive, that means that this difference is positive. So that means that f of x2 is greater than f of x1. So that means that f is increasing. If the x values are going up and then the y values are going up, that's exactly what f is increasing means. We chose x1 and x2 completely arbitrarily, so that proves that it's increasing in the entire interval. And if you want to prove the second half, you just change this assumption and just assume that f prime of x is less than 0 instead, and then you'll get that it's decreasing because you'll have a negative value. Let's find where the function f of x equals 3x to the fourth minus 4x to the third minus 12x squared plus 5 is increasing and where it is decreasing. So we will look at the derivative by the power rule. That equals 12x cubed minus 12x squared minus 24x, and we can factor out 12x. So we get 12x times x minus 2 times x plus 1. Okay, we want to know where this thing is positive and where it's negative, because that's where the function will be increasing or decreasing. So let's look for where it equals 0. So the derivative is 0 when x equals 0, that's this guy, or when x equals 2, that's this guy, or when x equals minus 1. So if I draw a little number line for x values, I'll put in minus 1, I'll put in 0, and I'll put in 2. I know that if I plug in a number to the left of minus 1, let's say minus 2, then this would be negative, this would be negative, minus 2 is negative, and this would be negative. A negative times a negative is a positive, times a negative is negative, so all of the numbers to the left of minus 1 would have to be negative. You might be saying, well, how do you know that all the numbers you just plugged in minus 2? But if we want to switch from negative to positive, that means that we'd have to go back up to 0 if we're negative. But there are no other zeros around except for this minus 1. So all the way to the left of minus 1, we must have a consistent sign. We have to have a consistent sign between any two zeros for the function. So if we go between minus 1 and 0, you could try plugging in, let's say, minus a half. Then this is negative, but this is now positive. So this is positive. Then if you want to try plugging in a number between 0 and 2, let's say 1, you get that this is positive, this is negative, and then this is positive. So negative times a positive times positive is negative. Lastly, throw in a big positive number, say 3, and then you get that they're all positive. so it's positive after 2. So these are values of f prime of x. Okay, you could also see, maybe if the derivative is negative, that means that the slope is going downward. If the derivative is positive, that means the slope is going upward. Negative downward, positive upward. So you could see that it's going to be decreasing on the intervals that are negative. So on the intervals from minus infinity to minus 1 and 0 to 2. So this implies that f is decreasing on these same intervals because the derivative is negative there by our increasing decreasing test. Let's look for where the derivative is positive. Okay, so that's on the intervals over here. So that's from minus 1, 0, and on 2 and above. So that's where f is increasing, the original function. Minus 1, 0, union to infinity. For our next test, we have the first derivative test. Suppose that c is a critical number of a continuous function f. That is, a number where the derivative is 0 or undefined. Then, if the derivative changes from positive to negative, we have a local maximum. If the derivative changes from negative to positive, we have a local minimum. If the derivative is positive to the left and right, or negative to the left and right, in other words, the derivative does not change sign, then f has no local minimum or maximum there. Let's find the local minimum and maximum values of the function in example 1. So remember that chart that we drew. Let's draw that again. So here's x. Here are zeros, minus 1, 0, and 2. It was negative up until minus 1, then positive, then negative, and then positive afterward. So we know that, and this is for our derivative f prime, we know that it was going down, then up, then down, and then up, because that's what increasing decreasing means. So it should make sense that if you look at the shape of the curve around minus 1, it kind of looks like that. So it makes sense that there should be a local minimum over there because it changed from negative to positive. It went down, and then it had to hit a point where it couldn't go down anymore, and the switch to go back up. So we could say that f of minus 1 equals 0 is a local minimum. Let's look at our next potential extreme value. At 0, it looks like we switch from going positive to going to negative. So it looks like there should be a local maximum over there, went from positive to negative. So at 0, we plug it in, we get 5, and we say that that is a local maximum. Remember, when we plug back in, we're plugging into the original function. We only use the derivative to see where the original function will have a local maximum in. We don't look at the extreme values of the derivative. Lastly, we could see that it's going down and then up for 2. So f of 2 is equal to minus 27, and that is a local minimum. Let's find the local maximum and minimum values of the function g of x equals x plus 2 sine of x. So we'll take the derivative, and we'll use our first derivative test. We get 1 plus 2 cosine x. So we're looking for when this derivative will be 0. Well, that's when cosine of x is equal to minus a half. We just solve for it. Okay, so let's draw a unit circle really quick. I want to see where cosine is minus a half. So let's say x value would be negative, so that should be over there. And it should be over here, the mirror image. So this is at 2 pi over 3, and then you keep going, and it's at 4 pi over 3. So we have 2 x values. Remember, we can't keep going past that because we're only from 0 to 2 pi. So x is 2 pi over 3, or x is 4 pi over 3. Okay, so let's plot these values. We're cutting our interval off this time at 0 and 2 pi. So this is x, and let's look at values for the derivative. We'll look at them around 2 pi over 3 and at 4 pi over 3. So up until 2 pi over 3, you're going from 0 to 2 pi over 3, it looks like the value of cosine will either be positive or it'll be a small negative number. So it'll be smaller than minus a half. So that means that if you look at the derivative, 2 times the cosine of x will be a smaller than negative number than 1. So it won't be able to beat this 1 to force the derivative to be negative. The derivative will be positive. If I look from 2 pi to 4 pi over 3, I keep going, that makes cosine a bigger negative number than minus a half. So this is a bigger negative number than 1. It's a bigger negative number than minus 1, actually. So that means that it's more negative than the 1. So our derivative will be negative there. And similarly, by the same argument as before, you go from 4 pi over 3 to 2 pi, and you either have a positive value for cosine or you have a small negative value. So our derivative will be positive there. So now let's look at those two values. Oh, by the way, this means that we're going up, then down, and then up. So you can kind of visualize where the extreme values are going to be. So if we plug in 2 pi over 3 for our function g, we get 2 pi over 3 plus 2 times the sine of 2 pi over 3, which is equal to 2 pi over 3 plus 2 times rad 3 over 2, because when cosine is a half, sine is rad 3 over 2, and this will be equal to 2 pi over 3 plus rad 3, which is roughly 3.83. So that is a, let's see, 2 pi over 3, we're going up and then down. It looks like a local maximum. Okay, we'll do 4 pi over 3 the same way. So g of 4 pi over 3 is equal to 4 pi over 3 plus 2 sine 4 pi over 3, which is 4 pi over 3 plus 2 times minus rad 3 over 2, because at that point sine is negative, the y value becomes negative over there. And we get 4 pi over 3 minus rad 3, which is about 2.46. So that is a local minimum. Because we go down until we can't go down anymore and then go back up. If the graph of f lies above all of its tangents on an interval I, then it is called concave upward on I. If the graph of f lies below all of its tangents on I, it is called concave downward on I. So that means that we've got the graph, we got all these tangents, like this, and the graph is lying above it. So it looks like it's going up, concave up, like a happy face. Similarly, if you've got all of your tangents lying above the graph is lying below all the tangents, then it's concave down, frowny face. So let's do our concavity test. If our second derivative is positive for all x in an interval, then the graph of f is concave upward. If the second derivative is negative, then the graph of f is concave downward. That should, I guess, make sense because you're looking at the rate of change of these tangents. So when you have that the second derivative is positive for all of an x interval, it should make sense that the graph will have to be concave upward over there. And when it's negative, it should make sense that the graph will have to be concave downward. That's how it forces the tangents to behave near the function. So the figure shows a population graph for Cyprian honeybees raised in apiary. How does the rate of population increase change over time? So when is this rate the highest? Over what intervals is p concave upward or concave downward? Well, how about we take a look at where the rate is starting at? If I try drawing tangents, they're below to begin with, but then they go above after. It looks like everything switches around over here. So let's estimate that point to be, let's say, 12 and 38,000 for the y. So we could say that the rate starts small, then notice it kind of goes up, picks up speed, so the rate gets larger until it looks like time equals 12, but then the rate starts decreasing, it starts leveling off. As it starts leveling off, notice that the slopes start approaching 0 as you keep going. So our rate is approaching 0 now. As the population, well, let's see, what is the population approaching? Looks like 75,000. As the population approaches 75,000. We call that the carrying capacity of the population, where the rate stops increasing, it just levels off. Well, not when it stops increasing, but when the rate just, when the population stops increasing. Notice the rate stops increasing at 12. When the concavity switches. So we could say that the population is concave upward on the interval from 0 to 12, right? Because it looks like a happy face over there. And then it switches to become a frowny face afterward. So it switches to concave downward after. Concave downward on 12 to 18. We called this point where the concavity switches from concave up to concave down, or concave down to concave up, a point of inflection. That's our next definition. A point P on a curve y equals f of x is called an inflection point if f is continuous there and the curve changes from concave upward to concave downward, or from concave downward to concave upward at that point. Let's sketch a possible graph of a function f that satisfies the following conditions. Okay, so let's look at what number 1 tells us. Well, if the derivative is positive on this interval, and the derivative is negative on this interval, then that means that it's increasing on the first interval and decreasing on the second. So f is increasing on minus infinity to 1, and it's decreasing on the interval from 1 to infinity by our increase and decreasing test. Then we look at what the second one tells us. The second derivative tells us about concavity. So this means that f is concave upward over here, because that's where the derivative is positive. So concave upward on minus infinity to minus 2 and 2 to infinity. And then it'll be concave downward on the interval minus 2 to 2. Okay, 3 tells us about some asymptotes. Remember that if the limit at infinity is equal to some limit, then that limit becomes a horizontal asymptote. So we have horizontal asymptotes at y equals -2 and y equals 0. Okay, let's try using this information to draw the graph. Okay, first let's put in our asymptotes. Y equals -2, y equals 0 is already there, that's our x-axis. And it seems like our function changes concavity at -2. So let's put -2 in there. It has changes from increasing to decreasing at 1. At 2 it changes concavity again. Okay, so it looks like, let's put in that inflection point at -2. Since we're approaching an asymptote and we're concave up over here, we can draw that. Concave up approaching the asymptote. Then we switch and become concave down all the way until we get to the next inflection point. So let's put the next inflection point over there. And keep drawing. Okay, so that was concave down from -2 to 2, and then we should be concave up again. And we have to approach our next asymptote at 0. So we're concave up, approaching the next asymptote. And that's just a rough graph of a function that meets all these criteria. Suppose the derivative is continuous near C. Then, if the derivative is 0 and the second derivative is positive, we have a local minimum there. If the second derivative is negative when the derivative is 0, we have a local maximum there. So let's do an example of that. Discuss the curve y equals x to the 4th minus 4x to the 3rd with respect to concavity, points of inflection, and local maxima and minima. We'll use this information to sketch the curve. So how about we let f of x be equal to x to the 4th minus 4x to the 3rd. Then let's take the derivative and the second derivative so that we can use our first and second derivative tests. So we have 4x to the 3rd minus 12x squared is equal to 4x squared times x minus 3 when we factor it out. So it should be easy to see where that's 0. let's look at our second derivative while we're at it. We'll have 12x squared minus 24x. So that's equal to 12x times x minus 2. Okay, so the derivative is 0. That if the derivative is 0, that implies that x is 0 or x is 3. So let's look for where our second derivative is 0. Well, our second derivative, we'll look for what happens to our second derivative at 0. Well, our second derivative, if you plug in 0, you get 0. So unfortunately, that tells us nothing about that point, because our second derivative test only tells us what happens if the second derivative is positive or negative. It doesn't tell us anything about 0. So we'll have to look at that case using the first derivative test. But at 3, it equals 36, which is positive. So that does tell us something. The second derivative says that f of 3, which is minus 27, must be a local minimum. Okay, so let's take a look at some of these values. We have 0, we have 3. We don't have to look at it past 3 because we already know that at 3 it's a local minimum, but we do have to look at it around 0. So if we go to the left of 0 for our first derivative, we could see that it's going to be negative. Try plugging in like -1, for example, and this is positive and this is negative. You could see that it doesn't matter if you plug in 1. If you plug in 1 instead, you go past 0, it's still going to be negative because, again, you're going to have positive and you're going to have a negative. So it looks like we're going down and we're still going down. Let's look for where our second derivative is 0 so that we can look for concavity now. So far we know that at 0 it's neither a maximum nor a minimum. If we can look at concavity, we can see if it's an inflection point. So x equals 0 or x equals 2, right? 0 or 2, that's when the second derivative will be 0. So let's make a number line for those. So we're looking at the second derivative to test for concavity. We see that if we plug in a number to the left of 0, let's say -1, then we get a negative and a negative, so that becomes positive. If we plug in a number from 0 to 2, then we get positive and negative, so it's negative. If we plug in a number past 2, let's say 3, then we get positive and positive. So that means it's concave up, concave down, and then concave up again. So if we look at 0, it switches concavity. And if we look at 2, it switches concavity. So we get 2 inflection points. This implies that 0, 0, and 2, if you plug it in, you get -16 for f, are inflection points. Okay, so I think we have enough information now to sketch the curve. We know we have a local minimum and we have 2 inflection points. Okay, so 1 inflection point is there. We also know that we have another one at 2, which is -16. And we have a local minimum at 3 -27. So here's 3 -27. Here's 2 -16. And here's 0, 0. We know that we are concave up until we hit 0, 0. Then we switch because 0, 0 is an inflection point, we become concave down. So we become a frowny face. Then we switch concavity again, because 2 is also an inflection point. We go happy face again, but this is a minimum. We stay concave up until we hit, whatever, good enough. That's X, that's Y, and this is a very, very rough sketch of Y equals X to the 4th minus 4X to the 3rd. Let's sketch the graph of the function f of x equals x to the 2/3 times 6 minus x to the 1/3. Alright, it looks horrible, because it is horrible. So taking the derivative is also horrible. So we're going to use a little bit of movie magic and just tell you what the derivative is. You can calculate it using the product rule. So we get 4 minus x to the 1/3 times 6 minus x to the 2/3. Ta-da! Again, let's use even more movie magic, because second derivative is even worse, because now you have to use the quotient rule. So we get minus 8 over x to the 4/3 times 6 minus x to the 5/3. Okay, let's look for where the derivative is 0. The derivative is 0 implies that x is 4, right? That's when the numerator is 0 for the derivative. For the second derivative, or actually, let's look, sorry, I forgot something about the first derivative. Notice that if you plug in 0 or 6, then that makes the first derivative undefined. So those are some more critical points. So the derivative does not exist when x equals 0 or x is 6. Okay, so let's look at all of these values, all these critical numbers. And let's see how, let's see what the sign of f prime looks like. Okay, so the sign of f prime, if we plug in, let's say, -1 to the left of 0, we can see that the numerator becomes positive. The denominator is negative and positive. Because this is to the 2/3 power, it's even, so it's going to be positive no matter what. So it looks like we have positive divided by a negative, which is positive. Sorry, which is negative. Positive divided by negative is negative. Okay, and then from 0 to 4, let's say plug in 1, we get positive and positive, so it's positive. And let's say we plug in 5. If you plug in 5, the numerator becomes negative. This guy's always going to be positive, and now this guy's positive, so we're negative. And if you plug in 7, it's the same thing. The numerator will still be negative while the denominator is positive. So it looks like it's going down, then it goes up, and then it goes down, and then down. Or it goes decreasing, increasing, decreasing, decreasing. So this means that f of 0, which is equal to 0, right around over here, is local minimum. And similarly, if you go over here, we have a local maximum. So plugging in 4, we get 2 to the 5/3 for f, and that's a local maximum. Let's look at our second derivative now. Our second derivative is undefined at x equals 0 and x equals 6. So let's look at those numbers. Okay, to the left of 0, well, this guy's going to be positive no matter what. And the numerator is negative no matter what. If we plug in, let's say, -1, then that makes this positive. So we have negative divided by positive is negative. So this is negative. Same thing if we plug in 1. Again, we'll have 2 positives in the bottom, and we'll have a negative up top. But if you plug in 7, then suddenly this becomes negative. So you get negative divided by negative is positive. Okay, and that's for f double prime. So that means that we are concave down still, and concave up. So there's no inflection point at 0, which makes sense because 0 is a local minimum, but there is an inflection point at 6. So 6, 0 is an inflection point. Okay, let's draw this guy. And we know that we have a minimum at 0. We know that we have a maximum of 4, and it's 4 and 2 5/3. So let's put some of these guys in. So 4 and 2 5/3. That's not going to be so good, but roughly around there. And we know that 6, 0 is an inflection point. So we should have an inflection point over there. Okay, we know that we're concave downward. So we're concave down up until we hit 0, which is the local minimum. However, notice it's still supposed to be concave downward. I can't go below because it's a minimum at 0. So I have to go back up, but I have to stay concave downward. So I go back up and I stay, and I stay concave downward. Staying concave downward until I hit 6, which is an inflection point. I have to switch now to concave up. Okay, so that's another very rough graph of y equals x to the 2/3, 6 minus x to the 1/3. Let's use the first and second derivatives of f of x equals e to the 1 over x together with asymptotes to sketch its graph. So you might remember when we were looking for limits for a function like this where it's not e to the x but it's almost e to the x, we would do substitution so that way we could actually figure out what the limit is because we know what the behavior of e to the x is. So let's do a substitution. Let t equal 1 over x. Well then, let's look what happens as x goes to 0 from the right, because that's the potential problem over here, where this thing's going to be undefined, is where we're going to have an asymptote. So as x goes to 0 from the right, we have that t goes to infinity. Remember that as x goes to 0 from the right over here, we get a really, really tiny positive number in the denominator. So dividing by a really tiny positive number is a really big number. So t gets really big. So now we can swap for our limit. As x goes to 0 from the right, for e to the 1 over x, that's now the same as the limit as t goes to infinity of e to the t, which we already know is infinity. That's just e to the really big number is a really big number. Okay, so now we know that x equals 0 is a vertical asymptote. I'll write VA for short. Okay, let's look what happens as we go to 0 from the left. Well, as x goes to 0 from the left, that means that t goes to minus infinity. So let's look at the limit. As x goes to 0 from the left of e to the 1 over x, we have that equals the limit as t goes to minus infinity of e to the t, which is, you might think, okay, that's going to be minus infinity, but it's not, because e to the minus something just makes it 1 over e to the something. So this is 1 over a giant number, which is 0. Dividing by a giant number is very small. So now let's look at what happens potentially as we go, infinitely in the left and right directions, to see if we have any horizontal asymptotes. So as x approaches plus or minus infinity, well, that means this thing gets really big. Again, if you're dividing by a really big number, you have a really small number, so t goes to 0. Either way, for large positive or large negative numbers. So that means the limit at whether or not x approaches infinity or minus infinity is going to be the same thing. It's going to be the limit as t goes to 0 for e to the t. So we can just plug in 0 because e is continuous, and we get 1. So we know that y equals 1 is a horizontal asymptote. Okay, let's do our derivative test now. The derivative, remember, for e to the x is just e to the x, so for e to the 1x is just e to the 1 over x. Then by the chain rule, we multiply by the derivative of 1 over x, so that's minus 1 over x squared. So this is minus e to the 1 over x squared. We draw our number line. We still have potential problem at 0. Okay, and it looks like to the left of 0 it's negative, because e to the 1 over x and x squared are both positive functions, so this negative out in front is going to force everything to be negative everywhere pretty much, except for at 0. At 0 it's just flat undefined because the original function is undefined. So there is no critical number here. It's just going down and undefined at 0. So there is no local maximum or minimum. Let's look at the second derivative. Okay, so we have to use the quotient rule. You can do that and get that it's minus x squared e to the 1 over x times minus 1 over x squared minus e to the 1 over x times 2x all over x to the 4th. So that can be simplified a little bit to e to the 1 over x times 2x plus 1 over x to the 4th. Okay, let's look at this number line for the second derivative. Okay, potential difficulties are at 0, again, undefined over there, whether you look at the numerator or denominator. But also notice now we actually have a point where the second derivative is 0 at minus 1/2. So let's look at that point too. To the left of minus 1/2, well, remember, these guys are always positive. So to the left of minus 1/2, this thing's negative. So everything's negative. And then once you go past minus 1/2, everything becomes positive and stays positive. So we're concave down, then concave up, and then concave up some more. So we do have one inflection point at minus 1/2. You plug that into the original function, you get e to the minus 2. So even though we have no maximum or minimum values, we do have asymptotes and an inflection point. I think that's enough information now to graph this thing. So let's put in our asymptotes first. Okay, we know that we have x equals 0 is a vertical asymptote, So that's our y-axis. And we know that y equals 1 is a horizontal asymptote. So that's y equals 1. We know also, though, that half e to the minus 2 is a point of inflection. So that's somewhere over here is an inflection point. We should be concave down up until that inflection point, but we should be approaching our asymptote. So we can try drawing that, concave down. Then it switches and becomes concave up. But it becomes concave up until 0, where it's not defined. So it's not defined at 0, and then we switch to concave up. Okay, for the rest of our graph, we are still concave up, but we're approaching this asymptote x equals 0. So we should be concave up, and then approach the other asymptote, y equals 1. Notice that we do not approach the asymptote from the left, because when we took that limit from the left, we got that it equals 0. It only blew up and equaled infinity when we went from the right. So when we go in from the left, we just approach this discontinuity right over there. And this is a rough sketch of e to the 1 over x.